All right, so here we have a little model, cute little model of the solar system. And this just shows a little bit of what's going on. One inner planet, maybe Mercury, and then the moon going around the Earth. So notice that this is a plane that these planets are in. That plane is parallel to the floor, the way that I've drawn this here. It's not to scale though. Remember, you could fit 1,000,000 Earths into the sun, so we don't want, but we just have this size so we can see these objects, and we're interested in objects like the Earth, so we can't have it 1,000,000th of the size of the sun and expect to be able to see it. Okay? But if we look at this from a top view, what we see is that all of the motions are counterclockwise. Looking down on the Earth's North Pole, you can see the Earth is rotating counterclockwise. The moon is going around the Earth counterclockwise. This planet is going around the sun counterclockwise. And the Earth's going around the sun counterclockwise. And so if you look up at the data projector, we can see that there's kind of a simple way to understand these planet motions, and that's simply to think counterclockwise, as viewed looking from above. And so here we're looking down then on the ecliptic plane. And so we're seeing then Mercury and Venus going around the sun, the Earth going around the sun, all counterclockwise, and most of them tend to rotate counterclockwise as well. Okay, and so the moon goes around the Earth counterclockwise, and most of the moons go around their parent planets in a counterclockwise direction. The only exception to this is Venus and Uranus do go around the sun counterclockwise, but they rotate on their axes clockwise. Okay? And there is a moon, Triton, that goes around Neptune, that also orbits Neptune in a clockwise direction. And so most motions are counterclockwise. So this includes all planetary orbits, all the major planets. It includes most of the planetary rotations. And the exceptions are Venus and Uranus. And also most moon orbits. And a notable exception here is Triton. Around Neptune. So these exceptions then are called retrograde motions. But here retrograde just means retro is in the opposite direction from what's normal. What's normal is counterclockwise. Now in order for this to be measured consistently, we have to be looking down on the Earth's North Pole. And so imagine now that this is the ecliptic plane, the plane of the board. And then the Earth is going around the sun like this in a counterclockwise direction within the plane of the ecliptic, and then the Earth is rotating on its axis this way. But you have to be looking down on the Earth's North Pole. If you were looking up on the Earth's South Pole, then everything would be reversed. So to keep things consistent, we have to do this in terms of this viewpoint, looking down on the Earth's North Pole. And then the moon is also going around the Earth in a counterclockwise direction. But for Venus, its rotation is clockwise, while its orbit around the sun is still counterclockwise. And so Venus then has what we call that retrograde rotation. If we get out to Neptune, the moon Triton goes around Neptune in a clockwise direction, so this is also retrograde. Okay, so we do have these exceptions, but the main motions, which, and this is going to help us later on when we are looking at the star wheel and identifying what's going on with our apps that help us to orient ourselves in the nighttime sky with stars, planets, and constellations. It's going to be helpful for us to know that these motions are counterclockwise, and I'll show you how we can tie that all together when we get to that section later on. Okay, now let's go back down to this picture here of the Earth-Sun system, and let's expand this out now until, let's imagine that this distance is what? This is about a foot, maybe. And on that kind of a scale, let's say that we want to go to the nearest star. Okay? And so where would the nearest star be if it were to scale so that the distance from the Earth to the Sun is about maybe a foot or a foot and a half here? Remember, that's 4,000 trips around the Earth or 400 trips to the Moon. Okay, that gets us to the Sun. And this is clearly not to scale. Okay. But if we just use this distance as being the distance from the Earth to the Sun, what I would have to do to get to the nearest star would be to jump in my car from here, and I'd have to drive all the way to Buellton to get to the nearest star. Okay? And so that is how much farther away the stars are in distance from each other relative to the planets. And so instead of talking about light hours, which was what we were talking about with the size of the solar system, now we're talking about light years. So let's just look at the data projector again. And let's see then how far away some of these distances are. Okay, so here the distance to the nearest star system, which includes Alpha Centauri, also Proxima Centauri, is part of a triple star system, our nearest star system. And of course, this is outside of the Sun. You go, well, what's the nearest star? And some people will say, well, the Sun. And, well, yeah, but here we're talking about the next nearest star. That would be part of the triple star system of Alpha Centauri, Proxima Centauri, and also there's a white dwarf star. And that distance, 250,000 times the distance from the Earth to the Sun. And so if we put that in perspective then with the scale that we looked at here, and that on that scale then we'd have to drive all the way to Buellton from here to get to the nearest star. We could think of it in another context as well. We have rockets that the fastest one right now that we have can go something like 40 miles a second. Okay, and so let's just think about that for a second. If it's going 40 miles a second, it's flying out of the solar system. It's one of the Voyager space probes, and it's got some gravity assists from other planets in order to help get it going that fast. If we had something like that nearby to the Earth, that would be 40 miles a second. We could get to Los Angeles if we wanted to go to Los Angeles, which is about, what, 200 miles away. So that'd be 5 seconds. A rocket that's going 40 miles a second could get from here to Los Angeles in 5 seconds. If you wanted to fly across the United States, say to New York City, it'd be about 90 seconds to get to New York City from here, going 40 miles a second. You take that same rocket and you point it at Alpha Centauri, it take you 75,000 years to get to Alpha Centauri. Okay, and so even with the fastest rockets that we have available today, it doesn't make sense to try to go there because it would just take too long for a trip like that to go to its conclusion. You'd have to either greatly expand your life expectancy, or you would have to freeze yourself away, suspended animation, but then you'd have to hope that the equipment would work to wake you up after 75,000 years, which is questionable. I don't know if I'd want to bet my life on that. You could experience extreme boredom for 75,000 years if we could find the genes that control aging, make you immortal. But it's just not practical. Even none of those solutions are particularly good ones for making a trip like that would take so long. But if we could go faster, which is possible in the future, there are other problems you run into. One of the problems is that, say you're going close to the speed of light, the smallest object hitting your rocket ship would be like a nuclear weapon going off. The kinetic energy of the collision would be catastrophic, and you would need incredible shielding just to protect you from the simplest little specks of dust and little marble-sized rocks that you would run into. And even more significant than that is Einstein's theory of relativity predicts that as you go faster, your time slows down. So the closer you get to the speed of light, the less you age relative to the universe that you're flying through at that high speed. And so what that essentially could mean is that you could go to Alpha Centauri and back, let's say in a couple of years, but you'd come back to an Earth that is hundreds of years older. Okay, and so you'd essentially be flying into Earth's future to try to accomplish such a to traverse such a large distance in a reasonable length of time. And so none of these solutions then are really acceptable. And so what we try to do instead is just be really clever about the way that we analyze the light that comes from these distant objects. And we haven't given up on trying to go there, but I think the best we can do for now is just to explore our solar system. That takes, in real time, just a few of our years, whereas going to distant stars would take hundreds of thousands to millions of years with our current technology. Or you run into problems with traveling into the future and nuclear-sized energy releases when the smallest objects hit your rocket ship. Okay, so let's go and take a look at the distances that are associated with Alpha Centauri then. Now we're talking about light years. Okay, so the distance then to Alpha Centauri is about 4 light years. It's a triple star system, and as we said, 250,000 times the distance from the Earth to the Sun. Okay. Now, the next biggest size that I wanted to look at is the size of the galaxy. Okay, so what's a galaxy? Well, you don't need to be an expert in galaxies yet, but we can define a galaxy as being a huge concentration of stars. So how big is huge? Well, our Milky Way galaxy has hundreds of billions of stars. Hundreds of billions. With a B. And so we haven't even had time to count these stars. Because if you counted one star a second, it would take you thousands of years, even at 1 star a second, to count hundreds of billions of stars. Okay, and so we're going to need computers then that can multitask and can count up multiple stars at the same time. That's the only way that we could possibly expect to do a reasonable survey of our Milky Way galaxy. Okay, and so if we look up at the data projector, here's an estimate of 400 billion. I've heard estimates of 1 to 2 to 400 billion. That's kind of a nice round number that we could start with. And so each of these stars is separated by about the same distance that we're separated from in our sun from the Alpha Centauri star system. Something like 5 light years distance. And our galaxy is what we call a pinwheel spiral. And so here's a picture then of the Milky Way, a galaxy that we think looks like the Milky Way galaxy. We, of course, can't take a picture of our own Milky Way galaxy because we couldn't travel far enough to get that kind of a shot. But we can look at other galaxies, and that is one of the main ways that we try to understand what's going on with our own galaxy. So this is looking at it from a top view. In the center we have a galactic nucleus, and then we have these spiral arms that are emanating out away from it. And so how far are we then from the center of our galaxy? Well, we think something like 28,000 light years. And our solar system orbits the galactic center once every 250 million years. Okay, so you might think then, well, it must be really taking its time. If it takes it 250 million years to go once around the center of our galaxy. But no, it's traveling about 140 miles a second. That's how fast our sun is going. And it still takes it 250 million years to get to all the way around. And so the distance across our galaxy from end to end is something like 100,000 light years. All right, so here is a scale model of our galaxy. And so we can see, looking at it from a side view, that it's flat. Very much like our solar system is flat along the ecliptic plane. And so in the center then we have the nucleus of the galaxy. And then looking at it from this side view, we have the galactic plane. And this contains the spiral arms, but looked at from a side view. So looking at it from a top view, we see the spiral structure, but looked at from a side view, we see a planar structure. Here's our sun and the solar system, and then this distance is about 28,000 light years. And here we'll abbreviate light year by LY. Okay, so let me just remind you that 1 light year is about 6 trillion miles. So the distance then to the nearest star, about 4 light years. But the distance all the way across the Milky Way galaxy is about 100,000 light years. So LY here is our abbreviation for light year. So the sun then is something like 3/5 of the way out from the center to the outer edge of our solar system. But how big is it? Is it this big? If I put a dot like that, does that represent how big the sun is with respect to the rest of the galaxy? No. You would need a microscope to see the sun on this scale. As a matter of fact, just to give you an idea of how big the galaxy is, with 100,000 light years across, what I'd like to do is just dot this eye. Okay, on side view here, so I dotted that eye. And so let's say that that little dot is the size of our sun. And now remember, you could fit something like more than 1 million Earths into that dot on that scale. And so if we consider that to be the size of our sun, on that scale, the distance across our galaxy would go all the way from here to New York City. That's how big the galaxy is. If a star, like our sun, is the size of that dot. Okay, and so that is, and the sun is 1 million Earths, right? And so that's just one galaxy. And there are trillions of galaxies that we've discovered, at least so far, in the known universe. And so now you're starting, I hope, to see, you may want to play that back again, because I can hardly even believe it, saying it now, and I've tried to get used to these distances for a long time, and it still seems almost unbelievable to me that something like that is possible, and that the universe is really that big. But that's what we're talking about. And so we're tiny, tiny in relationship to the size of the universe as a whole. All right, so let's go ahead then, and let's expand out a little farther, looking again at the theta projector. In order to see what's going on with our galaxy, we have a problem in that we're looking through the galactic plane, and so there's a lot of interference to our being able to view along a certain line of sight. And so this is the reason why we're uncertain to essentially a factor of 2 or 4 regarding how many stars there are in the galaxy. There's just so many things obscuring our view looking along the plane of the galaxy. But we can get an idea of what galaxies look like by looking at other galaxies, which we think are similar to our own. So now if we go to intergalactic distances, the distance to the nearest large galaxy outside of our own, which is Andromeda Galaxy, is 2.3 million light years. Okay, so the distance across our galaxy, 100,000 light years, but that's only 1/23rd of the distance to the nearest large galaxy, which is Andromeda. And so that's 2.3 million light years. It's also a spiral galaxy, and it contains a few more stars than ours. Ours is on the order of hundreds of billions, our Milky Way. Andromeda is about 1 trillion. And Andromeda and Milky Way are linked together by gravity and are the largest galaxies in a group of galaxies that we call the local group. Okay, so here's Andromeda. And so this star here is just an overexposure of a more nearby star. This was taken by pointing a camera at Andromeda Galaxy, and then this is before digital photography took hold, just keeping the shutter open and exposing the photographic plate for a couple of days while keeping the telescope pointed at the same spot in the sky. So we can see then that Andromeda is a very significant galaxy and is more what we call a pinwheel spiral, whereas our galaxy is a little more bar-shaped. But they're both flat galaxies, and Andromeda is a little bigger than our own galaxy. So they're both members of the local group. And that local group is about 3 million light years across. Okay, so let's just try to summarize a few of these most important points. Hope you're taking good notes. Okay, so this is the distance across our galaxy, 100,000 light years. Distance to the nearest large galaxy, about 2.3 million light years. Okay, now, interestingly, Andromeda can be seen without the need for binoculars or a telescope. You can see it as a fuzzy patch of light in the constellation of Pegasus, and it is the most distant object that is visible with the naked eye. But when we're looking at the light that comes from Andromeda, are we seeing what's happening on Andromeda now? No. Now we're looking a significant length of time into the past. We're seeing Andromeda as it was 2.3 million years ago. And if Andromeda could be looking at the Milky Way galaxy, then if we waved at them, they wouldn't see us for another 2.3 million years, because that's how long it would take for the light that is leaving us. We're saying, hey, how's it going? And they're not going to see that for another 2.3 million years. And so we can't really know what's going on in the universe right now. And there's a significant time delay, and that's the amount of time that it takes for the light to traverse that distance. Okay, and so that's related then to the distance by the speed of light. And something could have happened to Andromeda in the last 2.3 million years. We wouldn't know about it. Let's say a black hole came along and destroyed Andromeda galaxy right now. We would still see Andromeda as being normal for another 2.3 million years. And only then would we realize that something had happened, and then we could infer that that collision had happened 2.3 million years ago from the fact that it took the light that long to get to our eyes. So now that we're dealing with such huge distances, the amount of time that it takes for the light to get to our eyes becomes a significant factor. It's not a big deal when I'm looking at this pen, because I know that in a billionth of a second things haven't changed much. So I'm pretty much seeing the pen as it is now, to a reasonable approximation, even though I am looking a little bit back in time. But this becomes a huge limitation when we start looking at other galaxies, because we're going to be looking and seeing them how they were millions or even billions of years ago, because this is the nearest galaxy, and we're still seeing it as it was millions of years ago in the past, and not as it is today.